Right now, inside basically every piece of modern tech you own, there's an invisible war being fought. It's this constant, high-stakes battle against one of the most relentless forces in nature, heat.
And it's a battle we fight in our daily lives too, right? I mean, have you ever really stopped to think about how a simple thermos keeps your coffee steaming hot for hours? But then, on the complete opposite end of the spectrum, how in the world do engineers stop the processors in our crazy powerful devices from literally melting themselves into a puddle?
Well, the answer to both questions is actually the same. It all comes down to mastering the flow of heat, which is one of the most fundamental, unstoppable forces in the entire universe.
See, to control heat, you first have to understand its number one rule. And that rule is that everything in the universe is, well, kind of lazy. It always wants to reach a state of balance, or what scientists call equilibrium.
The core idea is incredibly simple. Energy always flows from a hot place to a cold place until everything evens out to the same temperature. You can't actually stop this from happening. All you can do is learn how to manage it.
Just think about it. If you leave a hot bowl of soup or a cold glass of water out on the table, they won't stay that way for long. The soup cools down, the ice water warms up, and they both creep towards matching the temperature of the room. That natural balancing act, that's heat transfer.
Okay, so if we're going to engineer a solution to control this, we've got to know our enemy. And it turns out heat makes its move in three very distinct ways. Let's break them down.
First up, we've got conduction. This is just heat transfer through direct touch. Imagine all the atoms in a metal pan are like tiny billiard balls. When you heat one end, its atoms start vibrating like crazy, bumping into their neighbors and passing that energy right down the line. That's conduction in a nutshell.
Next, there's convection. This is heat transfer through flow, and it only happens in liquids and gases. You know, when you see steam rising from a hot soup, you're literally watching convection happen. The soup heats the air right above it. That hot air rises, and cooler air swoops in to take its place. It creates a constant rolling current of heat.
And finally, there's radiation. This is the really wild one. This is heat that can travel through the total vacuum of space. It's the warmth you feel from the sun millions of miles away, or from a bonfire across the campsite. It's pure energy, traveling as invisible infrared waves. It doesn't need air, it doesn't need atoms to touch, it just goes.
Okay, so you have conduction, convection, and radiation all trying to make everything the same temperature. How do we fight back? Well, we don't just fight back. We get really, really clever. We engineer a solution.
And the primary weapon in this whole fight is the heat exchanger. Its job is simple, but absolutely brilliant. To purposefully and efficiently move heat from something you want to cool down over to something else that can carry that heat away. Now, there are a couple ways you can do this. You can have direct contact, like in a huge cooling tower where air and water mix. But for the really high-tech stuff, the magic happens with indirect contact. That's where two fluids or gases never even touch. They're separated by a super thin wall, and the heat has to pass through it. And that brings us to the next generation of this technology. Because the classic, old-school, bulky shell and tube exchangers from the past, they've been completely revolutionized by a much, much smarter design.
So, say hello to the modern plate heat exchanger. Instead of these big, heavy, clunky pipes, these systems use stacks of incredibly thin metal plates with special designs pressed into them. And the result? They are unbelievably compact, totally modular, and just ridiculously efficient.
So what makes them so much better? It really is all in the design. For starters, the plates are way thinner than old-school pipes, so heat can just zip right across them almost instantly. And their corrugated pattern, it creates intense turbulence in the fluid, which not only boosts heat transfer, but, and get this, it has a self-cleaning effect that prevents gunk from building up. And best of all, they're flexible. You need more cooling power? You just add more plates. It's that simple.
And when you look at the performance numbers, it is just staggering. This chart here shows the heat transfer coefficient. That's basically a report card for efficiency. The old shell and tube design clocks in at around 2,500. Not bad, but the modern plate exchanger, it's a massive 8,000.
So let's be super clear about this. The modern plate design isn't just a tiny improvement. It is over 3 times more efficient at moving heat. Now stop and think what that really means. A performance jump that big is what allows a data center to shrink from the size of a building down to the size of a closet. It's what makes compact, high-powered medical equipment possible. This isn't just better engineering, this is an enabling technology.
Now let's apply all of this to what might be the biggest challenge of all: cooling the tiny, incredibly powerful electronics that run our entire world. Because in this arena, the battle against heat is literally a matter of success or failure.
Here's the fundamental problem. As our computer chips get smaller and faster, the power density, that's the amount of energy we're cramming into a tiny space, it just goes through the roof. And this generates an immense amount of heat with absolutely nowhere to go.
And honestly, the stakes could not be higher. We're not just talking about your computer running a little slow. In critical applications like medical devices or aerospace systems, a thermal failure can be completely catastrophic. It's a mission-critical safety issue, period.
So to solve this, engineers rely on a whole suite of special materials called thermal interface materials, or TIMs. Their one and only job is to create a perfect gap-free bridge for heat to flow from the hot chip to its cooling system. But this is where the real design challenge comes in. It's a constant balancing act. Do you pick the thermal paste with incredible conductivity, but you know it's messy and complicated to apply in manufacturing? Or do you go with a simple thermal pad that's super easy to install, but you sacrifice a little bit of performance? Every single choice is a trade-off.
And, often the most elegant solutions are the ones that use no power at all. They're called passive cooling strategies. This is all about clever design, optimizing a heat sink to have the most surface area, using special coatings to radiate heat away more effectively, or even just shaping a device to encourage natural air currents, that convection we talked about.
So, from keeping our coffee warm to preventing our most advanced technology from failing, managing heat is one of engineering's greatest and most hidden challenges. But as everything gets smaller, faster, and hotter, this unseen battle, well, it's really only just begun. The real question is, what kind of innovations will come next?